In this video, we're doing proof by contradiction and the counterexample, higher level only. And the first thing to get straight is that these two do opposite jobs, because people reach for the wrong one constantly. If you want to show a statement is false, you need one example where it fails. One. That is a complete proof, and you are done. If you want to show a statement is true, examples are worth nothing. Last video, we watched 40 consecutive examples prove nothing at all. Those are opposite jobs. One counterexample kills a statement. 1,000 supporting examples establish nothing. And contradiction is the tool for the second job. So here's the method in 3 steps. Step 1. Assume the opposite of what you want to prove. Step 2. Reason carefully, forwards, until something impossible turns up. A number that is both odd and even. A fraction in lowest terms whose top and bottom are both even. Step 3. Conclude. The assumption caused that impossibility, so the assumption was false, so the original statement is true. And here's where it goes wrong. Before any maths happens at all, you have to negate the statement correctly. Take all primes are odd. The opposite of that is at least one prime is even. It is not all primes are even. That is a different statement. It is much stronger, and it is much harder to prove. Getting the negation wrong sets you off proving something you don't need and probably can't get. So negate it carefully, in writing, before you start. Example 1. And this is to show you how cheap the other direction is. Disprove. All prime numbers are odd. 2 is prime. 2 is even. Done. That is the entire proof. One line. And I want to be clear, that is a finished proof, not a sketch. Disproving is cheap. Proving is expensive. That asymmetry is the whole reason this video exists. Example 2. The counterexample from last video. Disprove. N squared plus n plus 41 is prime for every positive integer n. N equals 40 gives 1,681, which is 41 squared. Not prime. Done. Notice that finding it was hard, and writing it up was one line. That is normal. Hunting for a counterexample is the work. Presenting it is nothing. Example 3, the classic, and the one that gets examined. Prove that root 2 is irrational. Assume the opposite. Root 2 is rational. So root 2 equals p over q, where p and q are integers, q is not 0, and the fraction is in its lowest terms. That last phrase is doing all the work in this proof, so write it down. Now square both sides. 2 equals p squared over q squared. So p squared equals 2q squared, which means p squared is even. Now I need a small lemma. If p squared is even, then p is even. Why? Because if p were odd, say p is 2m plus 1, then p squared is 4m squared plus 4m plus 1, and that is odd. So an odd p cannot give an even p squared, so p is even. Write p as 2a. Substitute back. 4a squared equals 2q squared, so q squared equals 2a squared. So q squared is even, so q is even. And there's the contradiction. P is even and q is even, so they share a factor of 2. But we said the fraction was in its lowest terms. They cannot share a factor. That is impossible. So the assumption was false, and root 2 is irrational. Example 4. Same shape, completely different subject, which shows this is not a one-trick method. Prove there are infinitely many primes. Assume the opposite. There are finitely many. So you can list all of them, p1, p2, up to pn. Now build a new number. Multiply every prime on that list together and add 1. Call it capital N. Now divide capital N by any prime on the list. It leaves remainder 1 every time, because the product part was divisible and you added 1. So no prime on the list divides capital N. But every integer above 1 has a prime factor. So capital N has a prime factor that is not on your list. And the list was supposed to be all of them. Impossible. So there are infinitely many primes. And let's make that concrete. 2 times 3 times 5 times 7 times 11 times 13 plus 1 is 30,031. Now 30,031 is not itself prime. It is 59 times 509. And that is fine. That is not what the proof claims. Both of those are primes that were not on the list. The construction really does hand you new ones. Example 5. And this one teaches you when to reach for the method. Prove that if A is rational and B is irrational, then A plus B is irrational. Assume the opposite. A plus B is rational. Call it C. Then rearrange. B equals C minus A. But C is rational and A is rational, and A rational minus A rational is rational. So B is rational. But B was given as irrational. Contradiction. So A plus B is irrational. Now here's the lesson. Students try to prove that one directly and get stuck immediately, because there's nothing to grab hold of. Irrational is defined by what a number is not, and that is your signal. When the thing you are proving is a negative. Irrational. No solutions. Not divisible. Infinitely many. Assuming the opposite hands you something concrete to work with. That is how you know which method to pick. Negate the statement carefully. Reason until something impossible turns up. Then, say the assumption was false. And if what you are proving is a not or a never, that is your signal to reach for it. Next video starts the counting block. Permutations.